Hi, everybody. Let's take a look at Lab 2. We'll be looking at two different kinds of random variables and their distributions. First, we'll be looking at discrete random variables and then continuous, namely the normal distribution. So first off, take a look at the introduction text, gives you some guidance on what we'll be looking for in the lab, and then also want you to write an introduction for this lab based on what you've done. So first thing that we'll be doing is looking at probability mass functions and their cumulative distribution functions for discrete data. So remember that PMFs or mass functions are for discrete. We'll be looking at dice rolls here, the sum of two dice rolls. As before, we'll be using the pandas package to deal with data frames, and we're actually going to create our own data frame here rather than loading data. So to do this, there's this little loop here that will give us a data frame for the sum of two dice rolls. So we've got I, J, and then I plus J. And then we're saying I goes in between 1 and 7, but in fact, it's going to stop at 6. And then J does the same thing. So the way this is set up is that for each I, it's going to go I, 1, 2. So for each I, it'll keep I at 1. And then for all I1, it's going to go run J through 1 through 6. And then I moves on to the next one, so which would be 2, and then we get J 1 through 6. So that's how that works. And it nicely gives us all the possible outcomes of the sum of two dice rolls. So we get 36 from 0 to 35. Now what we'll do is use some functions to create a PMF. And to do that, we'll use NumPy, or NumPy, as some like to call it, the unique function. So what NumPy does, what the unique function does, is it goes into our data frame. So we give it the sum column, because that's what we're interested in. And then it returns counts. So it's going to find the unique sums, in this case, all the potential outcomes, and then it's going to give us counts for that. And the syntax here is unique comma counts. So it gives us two NumPy arrays with the two outcomes of this function. So the first one goes into unique, and that gives us the unique sums, 2 through 12. And then it gives us the counts of all those. And that way we are able to get the frequency, basically a histogram. Now to convert this into a PMF, we need to simply divide each of those individual counts by the sum of the counts. And that gives us the relative frequency. So we'll define the PMF as the relative frequency of each of these. And here's what that looks like. And then if I add sum of my PMF, guess what that should be? Oh, I got to run all this. That should be, of course, 1. So it sums to 1, approximately. All right. So on your own, please plot the PMF using a stack plot, or a stem plot, rather. We did this in lab 1, so you can go back and look at that code. And then make sure you plot your x-axis and your y-axis appropriately. Then we'll create a cumulative distribution function and plot that as a step plot. So we can use the cumSum function over our PMF and to cumulatively sum up the values of that. And then we can plot it as a step plot or a step plot. So I give you a link right here on how to do that. And there's different ways to assign where the step's going to occur. For a cumulative probability function for discrete variables, we want the step to occur at the end of the interval. And so there's a where argument within the step plot function that you're going to set to post. So click on this link and it'll bring you to the matplotlib package that will allow you to use the step plot function for that. So go ahead and do that, and then calculate the probability based on the CDF of the sum of two dice rolls not being 7. So you can use the symmetrical properties of this to calculate that. So show your work in a code cell and provide your answer and your response in a markdown cell, please. So that's all we're going to do for the PMF and cumulative distribution function. I will stop the video here and do another one for the normal distribution or continuous functions.